I welcome you to another session of Module 4, that is Quantum Mechanics and Lasers, wherein we will be discussing the concept of interaction of radiation with matter and also Einstein's coefficients. In this session, we will be covering the topics interaction of radiation with matter, under which head we will be discussing first induced absorption, then spontaneous emission, afterwards stimulated emission. And next we will be covering Einstein's coefficients. First of all, let us know in brief few important applications of laser before going further. So laser plays a very important role in communication system. Without a laser, whatever today we are enjoying so-called highly advanced communication system is totally unimaginable. Nowadays, BSNL, Jio and some other companies are providing very high-speed internet to homes and offices in the name of FTTH or Geo Giga Fiber or FiberNet and so on. So all these very high-speed internet connections are possible only due to the optical fiber communication system, wherein laser is playing a very important role. Next, in the field of defense, laser is used as weapon as well as surveillance system. In the laser weapon system, in short, it is called as LOS. Laser weapon system, in short, LOS, is already in use by US Navy. And we can see in this picture, which is mounted on top of the ship. So this is a LOS, laser weapon system, which is mounted on the top of US Navy ship. In this LOS, the laser beam fired from that LOS is so powerful that it's enough to destroy the target and also just disable its equipment. Further, in the field of surveillance, the laser is being used as a space surveillance systems. With the help of satellites and other equipment, it is possible for us in early detection of enemy's missile and planes. A laser beam is used in airborne lidar technology to measure the topography of the ground with the help of GPS and IMU systems, providing location and orientation of airborne platform. Here, lidar means light detection and ranging. And here this application of lidar that is there for your syllabus, and we will be discussing in the applications of laser. Next, laser is being widely used in many industries, such as it is used for cutting, drilling and welding purpose. Here in this figure, you can see laser is being used in precise cutting of the metal pieces. So here you can see some portion of the metal pieces are cut into precise geometrical shapes here. And cutting is very precise, and here one of the advantage of laser cutting is over the manual cutting is here it is a non-contactless process. Manual cutting is contact process, wherein the wear and tear of the tool parts happens. But here such a thing will not be there. Wear and tear is totally absent. Though we have discussed many important applications of laser, we should know that laser stands for light amplification by stimulated emission of radiation. So here light gets amplified or boosted by the process of stimulated emission of radiation. And this stimulated emission of radiation is a particular consequence of interaction of radiation with the matter. So now let us discuss interaction of radiation with the matter. So this interaction of radiation happens under three heads, and the interpretation of this interaction is done on the basis of energy level diagram. So here first we will be discussing the interaction of radiation under these three heads. So first will be induced absorption, next spontaneous emission, then stimulated emission. So first let us discuss induced absorption. So consider an atom in the energy level E1. Consider a single atom in the energy level E1. So this is an atom. So this is the energy level E1 wherein it is staying, and this is the lower energy state. So when this atom absorbs a radiation of a frequency nu, a suitable radiation of frequency nu, after absorbing it will go to the higher energy state. It makes a transition from that state 1 to state 2, that is a E1 to E2, that is called as a higher energy state. So here it makes a transition from lower energy state to higher energy state. The number of such absorption per unit time, per unit volume is called rate of induced absorption. So here what the transition we discussed right now, this is for a single atom. So if I take that rate of absorption for a matter as a whole, so there will be a trillions of such atoms will be there. So if I talk about the rate of absorption for that matter, so here that is the rate of absorption that is taken per unit time, so for a given second or per unit time, so per unit volume, in the unit volume. So how much of absorption is happening there? That is called as a rate of induced absorption or simply rate of absorption. So the rate of absorption, on which factor it is depending? So this is a induced absorption. So on which factor it is depending? So first one, it is depending on the number density of lower energy states. So how many atoms are possessing this state of energy? So here it is not only it's not enough only the presence of atoms that must be there in the lower energy state. There should be an appropriate amount of energy that must be there. Okay, so not only the number of energy levels that are there in the lower energy state, it also depends upon the energy density U nu. So here this can be written mathematically as the rate of absorption is directly proportional to N1 and U nu. Okay, here the rate of absorption, if you remove that proportionality constant, proportionality by a constant, so we'll write that N1 U1 by replacing that proportionality with this constant B12. So here this B12 indicates the transition from lower energy state 1 to higher energy state 2. So B12 is a constant of proportionality called as Einstein coefficient of induced absorption. So next discuss spontaneous emission. An atom, consider an atom in the energy level E2, that is a higher energy state. Now this atom which is present in the higher energy state undergo a transition to lower energy state E1 spontaneously on its own like this. So it makes a transition from higher energy state 2 to lower energy state 1, that is a E2 to E1. So here this transition is a voluntary process, means it does not require any external aid. So without any external energy, here it is making a transition from higher energy state to lower energy state. So while coming from higher energy state to lower energy state, it emits a photon of energy nu. Okay, so it emits a photon of energy nu. So suppose that, for example, so if the atom energy value here is suppose 6 electron volt and the energy value of this is 3 electron volt. So here to occupy the state from this 6 electron volt state to 3 electron volt state, it has to give up the 3 electron volt of energy, which is an energy difference of these two states, which is the energy difference of these two states. So when it is going to occupy this 3 electron volt of energy, it has to give out this out of the 6 electron volt, it has to give out 3 electron volt of energy. Okay, why? Because here it is having a 3 electron volt value. So to have this seating, so to occupy this energy state, it needs to give out that extra 3 electron volt of energy. So this is a voluntary process, and it is independent of the energy density of the incidenting radiation. So here this is for a single atom again, and if I talk to a bulk matter, then I need to talk the rate of spontaneous emission. So number of such emissions per unit time per unit volume is called as a rate of spontaneous emission. So this is a rate of spontaneous emission. So this depends on the number of atoms that are there in the higher energy state, that is called as a number density of higher energy state, that is N2. So this is how many number of atoms are there in the higher energy state, that is represented as N2. So this is the higher energy state. So it depends on the number density of atoms in the higher energy state. So that is mathematically it is represented as rate of absorption is directly proportional to N2. So when I remove this proportionality constant, the proportionality by a constant, I have to add this constant A21. So 21 representing a transition from second energy level, that is higher energy level, to lower energy level 1. Okay. So here A21 is a constant of proportionality called Einstein coefficient of spontaneous emission. So next, stimulated emission. Third one is a stimulated emission. An atom in the level E2 makes a transition to lower energy state E1. So here the atom in the higher energy state makes a transition from higher energy state to lower energy state by the help of an external aid. So with the help of external aid, the atom makes a transition from higher energy state to lower energy state. So by absorbing this external energy nu. So when this absorbs external energy nu, so it makes a transition from energy level 2 to energy level 1, like this. So after when it makes a transition from higher energy state to lower energy state, so it has to give up some extra energy. Okay. So here it will give out 2 photons in this process. So this one photon is already present due to the external energy that what we supplied. This is the photon actually, and this photon, another photon, is due to the transition happening from higher energy state to lower energy state. So totally there are 2 photons that are emitted during this stimulated emission. So number of stimulated emission per unit time per unit volume is called the rate of stimulated emission, and this depends upon 2 factors, that is the number density of higher energy state, that is N2. So how many number of atoms that are there in the higher energy state E2, and the energy that you are supplying, that is external energy density that is you are supplying there. So rate of absorption is mathematically written as, so it is proportional to how many number of atoms are there in the higher energy level N2, that is, and also the appropriate amount of energy that need to be supplied, that is a U nu. So now if I remove that proportionality by a constant term, here B21, so again 21 represents the transition happening from higher energy level to lower energy level, and N2 U nu as it is. Okay. So here B21 is the constant of proportionality called Einstein coefficient of stimulated emission. So till now what we discussed is the interaction of radiation with matter under 3 heads, that is induced absorption, spontaneous emission and stimulated emission. So now based on these concepts, now let us discuss Einstein coefficient, that is also called as expression for energy density. So Einstein explained the basic mechanism involved in interaction between radiation and matter. So in his studies, he assumed that matter is in thermodynamic equilibrium with black body radiation field. Hence, the total energy of the system remains unchanged in spite of various interactions taking place. Here, you should know the black body is one which is a good emitter and a good absorber. And a perfect black body is called as a body is called as a perfect black body if it has the capacity to absorb 100% of the incidenting radiation, and also it has the capacity to absorb the 100% of what it has absorbed, that radiation. It has the capacity to re-emit all that incidented radiation. So a perfect black body is a complete emitter and a complete absorber. So here Einstein compared a matter is in thermodynamic equilibrium with that black body radiation field. So here, when it is in equilibrium, a matter is in equilibrium, then the total energy of the system remains unchanged in spite of the various interaction, that is whether it may be induced, spontaneous or stimulated emission. So all these three processes might be taking place there. In spite of that, the total energy of the system remains unchanged. Say at thermal equilibrium, so rate of absorption is equal to rate of emission. So here at a thermal equilibrium, rate of absorption is equal to rate of emission. For example, let us understand this by taking a water tank. Suppose there is a water tank and it is having an inlet and outlet. Suppose if you have blocked the outlet and only you have opened inlet and you go on keep pouring the water through the inlet, so what happens? So it will fill up its level up to a particular the maximum level and flows. Okay, so what is happening? Only there is a filling. So the filling up of water, you compare that to a energy. So you are supplying that water tank, you compare it to a matter. So you are supplying that continuously energy to a matter. Okay, so now it is a absorption. It is taking the water is you are feeding it to a water tank. So water you are feeding it to a water tank. So only there is an absorption, or there is an intake of water. Now the water level during that intake, when it is at zero, so as you go on pouring the water, the level is going to increase. So total volume at the end got increased. Suppose that water tank, you have opened the outlet, and also you have opened the inlet, and here how much quantity of water that is coming into the water tank is same as that of the outlet water. So how much quantity of water that is coming in, the same quantity it is going out. So what happens to the total volume of the water now? Yes, the total volume of the water remains the same, unchanged. So how much quantity that is coming in, so much quantity going out. So total volume of the water remains unchanged. So in the same manner, though the matter is interacting with the radiation, so energy is falling in and it is absorbing after falling. At the same time, it is giving out by emitting a radiation or a photon of radiation of some frequency. So there is a continuously emission and a absorption. Both are happening simultaneously. So in such a case, what happens? At equilibrium, rate of absorption becomes equal to rate of emission. So here, the rate of absorption is of only one kind, but the rate of emission, it's of two kind. That is rate of spontaneous emission and a rate of stimulated emission. So emission process happens under two heads. So it may be either spontaneous or it may be under either stimulated. So now, earlierly discussed the rate of absorption. So we already had a equation set up there. So we are taking the same equations here as well. So rate of absorption is given by B12 N1 U nu, and rate of spontaneous emission is given by A21 N2, and the rate of stimulated emission is given by B21 N2 U nu. So now here what I did is I kept B12 N1 U1 as it is, and I brought this B21 N2 U to LHS. So what happens here when I bring it to LHS? So plus term becomes negative. So here it is a negative. And I kept A21 N2 as it is. A21 N2 as it is. So here in this term, so our aim here is to derive an expression for energy density. So U nu is energy density. So I want this U nu actually. So here from these two terms I am taking U nu common, and remaining terms I am writing as it is. Remaining terms I am writing as it is. So here when I take U nu out, here in the first term I left with B1 to N1, B1 to N1, and here in the second term B21 N2, B21 N2, and the right hand term as it is. So here I have written the same term here once again that was there in the previous slide. So here I am just keeping this U nu at LHS and bring this term to RHS towards the right hand side. So what happens here? So you just cross multiply. What happens? A21 N2 divided by B12 N1 minus B21 N2. So rearranging the above equation, we get here what I am doing is I am rearranging this equation. So here what I am doing here is in this term what I do here is I am taking this A21 term that I am keeping it out and bringing this numerator term N2 to denominator here. That's what I did here. I brought that N2 to denominator. So what happens here? I am distributing that N2 to each term here. So this is B1 to N1 divided by N2, B21 N2 by N2. So here N2 in this term cancels out and I left with only here B21. And this term as it is, I have written here. So what I did here is I took just that B12 out and I grouped this N2 by N1. It is the same. So here I took back the same term here that was there in the previous slide. Here in the next step what I am doing here is I am taking this B12 out. Okay, I am taking this B12 common. So here after taking common here B21, so here I left with in the first term B12 by B21. So if you just multiply this B21 to this first term, what happens? B21 cancels. I left with as it is B12. So here when I take common out, so I am writing here B12 B21 and another term as it is, and minus 1 I left with minus term in the second term. So why? Because I have taken this out common. Say this is equation 1. By Boltzmann's law we have N2 by N1. So N2 represents the number density in the higher energy state, number of particles present in the higher energy state, and N1 represents the number of particles in the lower energy state. So the ratio of N2 to N1 is derived as e to the power minus E2 minus E1 by kT. So E2 minus E1 is the energy difference of E2 to E1, energy difference of these two states, E1 and E2. And here this delta E, so E2 minus E1, that is can be written as delta E. So delta E is also written as h nu. E is equal to h nu, or delta E is equal to h nu. So e to the power minus h nu by kT. So N2 by N1 can be written as e to the power minus h nu by kT. That is, if I just interchange this Boltzmann's equation here, this is N2 by N1, but I want here N1 by N2. Why I want in this form? See here, in the equation 1, I have N1 by N2. Okay, I have a factor N1 by N2. So I want here this Boltzmann's equation not in the form of N2 by N1, but I want in the form of N1 by N2. So just cross multiply this. okay, in the above equation. Just cross multiply. So what happens here? So n1 by n2 that you are taking in the numerator, n2 to denominator. So this goes to denominator. So here 1 divided by e to the power minus h nu by kt. So when it goes to numerator, so here we left with e to the power plus h nu by kt. So here n1 by n2 is e to the power h nu by kt. Now equation 1 becomes, so that equation we are substituting that value n1 by n2. So here we are substituting that value here in that equation 1. So this is the equation after substitution. Say this is equation 2. Now according to Planck's law, since we have considered our matter is in thermodynamic equilibrium with black body. So Einstein derived an equation for black body radiation. So according to him, U nu, that is the energy density of black body radiation, nu is given by 8 pi h nu cube by C3 cube into 1 divided by e to the power h nu by kt minus 1. Say let us this equation as 3. Now compare LHS of equation 2 and LHS of equation 3. So these are the LHS. So here in the equation 2 there is a presence of U nu and equation 3 U nu. So here both are same. Okay, energy density, both are energy density, they are same. Then RHS must be equal. Now here we compare this RHS term by term. So here this is a coefficient. You compare this coefficient with this equation 3. So here you see you compare this term with this term. So 1 and 1 they are same. So here e to the power h nu by kt, e to the power h nu by kt they are same. 1 and 1 minus 1 minus 1 it is same. So here the coefficients term must be equal. So here a21 b21 this term must be equal to this term, that is 8 pi h nu cube by c3 cube. So these two must be equal. In the same manner here beside this e to the power h nu by kt, so there is a factor here 1. So 1 must be equal to this b12 by b21. So these two must be same. So b12 by b21 that must be equal to 1 here. So I'll write that is a21 b21 is equal to 8 pi h nu cube by c3 cube and b12 by b21 is equal to 1. So here in this term just if cross multiply this term b21 to RHS. So what happens here is b12 becomes equal to b21. So in the next slide that is b12 is equal to b21. So in the next slide I am considering that one. B12 by b21 is equal to 1 and another equality here a21 b21 is equal to 8 pi h nu cube by c3 cube. So that is equal to b12 by b21 is equal to 1, that is equal to b12 is equal to b21. So this implies that the probability of induced absorption b12. So 1,2 represents the absorption process. So 1,2 is a induced absorption. So that is equal to the probability of stimulated emission. So this is the meaning of that term. The probability of induced absorption is equal to the probability of stimulated emission B21. So because of the above equality identity, the subscripts could be dropped and A21 and B21 can be represented simply as A and B. And equation 2 can be rewritten at thermal equilibrium of energy. This is the equation 2 actually. This is equation 2 that can be rewritten as U nu is equal to, so here this is a A21, so that I am writing A21. So A21 instead of A21 directly I will take A. So B21 directly I will take it as a B. And here B1 to B21 that is equal to 1. So this is equal to 1. So I am writing this is a 1. So remaining term is e to the power h nu by kt minus 1. So this is called as the expression for energy density. And let us say this is equation 4. So equation 4 represents expression for energy density. So here in this session, we discussed first interaction of radiation with the matter, under which we discussed what is a induced absorption, what is spontaneous emission, then stimulated emission. Then afterwards, we discussed expression for energy density. Thank you.